Okay, let me get started 1 minute early. Oh no, just in time. We are going to be discussing linear algebra today. So it's kind of a review. We are going to go a bit fast in some stuff. It's quite basic, but we are going to try to make contact more explicitly with the things that we are going, with the tools that we are going to be using on next class and in the following class. So we will have 2 lectures about this. So the first one is going to be today. So we will have a review. We will have some reminders of how to solve a linear system, their properties, different kind of solvers, and different kind of structures for matrices. We touched about this, or we discussed about this a bit last class when we saw the PDEs and we saw this kind of banded matrix that come after the operator that we use for discretizing the spatial part. And next Thursday, we are going to be talking about which are the packages that you can use for actually implementing and solving all the things that we are going to be talking about today. In particular, we are going to be talking about BLAS and LAPACK, or CBLAS and LAPACK-E, which are the C versions of these libraries. But there are a bunch more. Okay. So kind of what we did last week was a bit of a motivation for all the methods that will come after. And starting this week is mostly linear algebra. But the truth is that linear algebra doesn't show up only in the differential equations. It shows up in a lot of different fields and topics. Linear algebra per se is a whole topic that it can be solved numerically, like if you need to compute eigenvalues, eigenvectors, stability of systems, I don't know, a lot of things. Even if you are doing statistics, you have covariance matrices. It's all over the place, basically. One of the things that we like to emphasize in this course is if there is something, if there is a tool that is already in place and you can use it, please do it, because it will save you time. Probably that tool is well developed, in the case of the libraries that we're going to mention. It has been prone of errors, it has been prone of bugs. So that is kind of our take-home message from this course. So we're going to see more about that next Thursday. By the way, I'm going to be posting the assignment today after the lecture. It will have a bit of linear algebra and a bit of what is coming on Thursday. So just take a look at it. Probably you won't be able to, maybe one of the parts, but not all the parts you will be able to solve, but just take a look at it. So let's start with the review. Okay, very basic, vectors, right? Any linear algebra course starts with the concept of vectors. The easiest or simplest interpretation is the geometric interpretation, where we can think of a vector like an arrow pointing in certain direction with a given length. And then you have operations that you can apply to the vector, like scaling a vector, adding vectors, subtracting, multiplying in many different ways. You can do dot products or inner products, scalar products, outer products, all kind of different things. Okay. The interesting thing with vectors is that starting with this simple concept, you can construct vector spaces. And things there get a bit more interesting, because then you can use vector spaces for whatever you think. Quantum mechanics, solid state physics, you name it, it's also everywhere. So the vector spaces is constructed by this object, a vector, which we like to represent like an arrow in 3 dimensions, if you wish, but it can be n-dimensional actually, right? You only need to have n components of these vectors. If you wish, you can even think about that as the arrays that we use to represent in C++ or in any computer language. But basically the idea is that there is a basis which gives you the dimensionality of the space. The basis has some properties, like they are linearly independent. It means that you cannot construct any of the vectors in the basis combining the other vectors of the basis. Okay. The formal definition of a vector space, it has 4 elements. It has to have a body, which is the scalars that you use, that is represented with the letter K here. It has to have the set of vectors that you use to generate the space. And then it has to have 2 operations, the plus and the scalar product. Okay. As an example, you can have the space of vectors given by all the real components in an n-dimensional space, while the body, it can be either reals or complex, meaning the factors in front of the vectors can be either real or complex. Okay. Considering these vector spaces and the generalization of the concept of vectors, some nice properties start to show up. For instance, when we say that two vectors are orthogonal, it means that the inner product, depending on the definition of your inner product, gives you 0 if and only if the vectors are different. Okay? And you say that these are orthonormal, that they have been normalized, if the inner product between the same vector is 1. That is a very easy property to achieve, because all what you need to do is to divide over the length of the vector, and that is it. Okay. So one of the consequences of this is that a set of n orthogonal vectors will necessarily expand the vector space they generate. So that is kind of a circular condition between a basis and a set of linear independent vectors and orthogonal vectors. Okay. Now, after we are happy with the concept and we get familiar with the concept of vector spaces, there is another player that comes into place, and these are the matrices. And matrices are very interesting because, again, first approach that you may want to have with matrices is maybe this rectangular shape where you have columns and rows, and you can do operations with vectors like multiplications between vectors and matrices. And the operation is quite simple, right? You have these rules where you take one column from the matrix and you multiply by the first element of the vector, and then you start to add successively each of them. Now, there are other interpretations associated with the matrices, and one of the interpretations that is pretty nice is actually that matrix can operate into one of these vectors and create some sort of operations, like a rotation. It can also scale the vector. If you give a particular shape to the matrix, it can operate in the vector, like shrinking or expanding it or rotating it. So this is related, so if you do some sort of physics like mechanics, this is related to the active or passive interpretation of coordinate exchange, for instance. The nice thing is that when you have equations like ax equal b, being x and b vectors, if x is the unique vector of coefficients, then you can interpret these columns as the basis of the representation of the vector. So another way to say this is, if this is my x, y, and z axis, the coefficients are basically the coordinates of the vector. So it can be used also for projecting the vector into the basis of the vector space. Okay. And then this is kind of review. You probably have covered this in other courses, because exactly this idea is that you can say that the column space of the matrix is basically spanned by the vectors that represent each of the aces in that vector space. Okay, and so any vector in the vector space, if these are bases of the vector space, can be represented by a linear combination of the matrix with coefficients, appropriate coefficients in the matrix. Okay. So there is another way to interpret the matrices, and this is quite powerful as well, is to think about matrices as linear transformations. Okay. So if I take a vector x and apply the matrix A, so that can be thought, actually there is a mathematicians like to call a diffeomorphism between a linear transformation and the matrix multiplication. Which properties this transformation should follow? Well, it has to be linear. So if I have two vectors that I apply the same transformation, this is the same to apply the transformation to the addition of the vectors, or just apply first and then add. And similarly with the scalar. So I can apply, I'm sorry, this should be a b here. I can put the scalar outside. The scalar has to belong to the body of the vector space, but I can put the scalar outside. So there is this idea that linear transformations can be thought as matrices, and they are also named linear operators as well. Okay. Again, this shows up in many different fields, in quantum field theory, in quantum mechanics, even engineering. When you do tensors and you associate tensors with matrices, is in different fields. Now we move into the arena of the linear transformations. One of the nice things is because of we talk about the linear independence of vectors that formulates or expands the vector space. Associated with that, if we have the matrix which contains somehow a representation of the basis of the vector space, we can associate the range of the matrix with the dimensionality of the vector space. How we would do that? Well, there is this quantity range saying that if a vector belongs to the range, then we can prove that there exists one vector such that A applied to that vector will give us B. People call this also the image of A. So all the vectors in the vector space should be achievable by the matrix that generates that vector space. Okay. Again, think about this as the idea of these column spaces that spans basically the vector space. Any questions? I'm going fast because I assume that most of you have seen this concept before. Okay. This is another interesting concept associated with the linear transformations or operators. What is the null space of a matrix A? Well, it's basically all the vectors that give you the null element in the vector space. That's a property I didn't mention, but all the vector space have to have the null element included there. Why? It's very simple, right? If I choose to have a scalar that is 0, at the end I will get the 0 element of the vector space. So the null element has to always be in the vector space. So the null part of the transformation is all the vectors x that goes to the 0, but of course x cannot be 0, otherwise it's the trivial transformation. Okay. The interesting thing that we can prove is that for matrices that has a non-empty null space, there may be a solution for the system AX equal B that has either infinite solutions or no solution at all. Okay, so it's an undetermined system in that way. Okay. The other thing that we can prove, I didn't mention this here, is that is the matrix that spans the vector space. Probably the dimensionality of the vector space is not n. And even more, I can prove that one of the column spaces is a linear combination of the previous column spaces in the matrix. Okay. And somehow the vector space is overdimensioned in that way. Okay, this takes us to the idea of the rank. So we talk about the image and we talk about the rank and the null space. So the rank of the matrix is basically the dimension. It's how many dimensions the matrix has that are linearly independent. In other ways, it's the minimum number of bases in the vector space that will span the vector space. So I can give you a matrix that is dimension m, but the vector space is dimension n, and n should be less than m, so they have more columns than the vector spaces, the number of vector spaces in the vector space. So for square matrices, if my matrix is formed by the column spaces, it has to have the full rank of the vector space. So the rank has to be n. In general, what happens is that the rank of the matrix plus the rank of the null space, which is equal to the number of independent columns in the matrix, has to be equal to the dimension of the vector space. Okay? So this is a nice formula that you can keep in mind when probably you have used it for solving linear algebra problems or something like that. Okay? So we have been talking very quickly about vectors, matrices, vector spaces, properties associated with that, linear transformations. And now we are going to focus a bit more on the matrix side of the transformation, on how to see that. And you have seen that probably that if we have a matrix, you can compute the inverse of the matrix in many cases, not always, but in many cases. And the definition is basically, I had a matrix such that if I had the matrix multiplied by another matrix, and that gives me the identity, then that is the inverse of the matrix, right? And only in this case, or not only in this case, but commutation of factors in matrix multiplication is not always true, right? So only in this case you can actually play the role of inverting the order in the multiplication, and that should give you the same, because at the end you get the identity. There are associated, again, if you take the perspective of the linear transformations, or you take the perspective of matrices, this has very nice interpretations, because when I say the inverse of the matrix, I mean also the inverse of the transformation, meaning that if I take a vector and I transform into something else, I can come back from that transformation and get my original vector. So associated with the concept of the inverse for a n by n matrix is the case that the rank of the matrix has to be equal to the dimension of the vector space. The range of the matrix is equal to, in the case of real numbers, I think we're going to focus mostly in Hermitian matrices, which are matrices that are represented by real numbers, is r to the n. It's the same to say, because of the equation that we saw before, the null subspace of the matrix is null, is void. There is no element, there is no vector in the null subspace. In terms of eigenvalues, and we're going to see what that means in a second, there are no null eigenvalues. All has to be positive or negative at least. There are no single values, and more importantly, this is a very easy check to do. The determinant of the matrix is non-zero. If you remember again from the linear algebra courses, there is a way to compute, at least for square matrices, the inverse of the matrix as a function of the determinant, where it's in the denominator of the expression. So if that is 0, basically give you a non-defined inverse for the matrix. Okay. Interestingly, some of these concepts can be generalized to rectangular matrices, where the matrix doesn't need to be n by n. You can have a matrix which is n by m, and the idea is that you will have a pseudo-inverse matrix in that case. Okay. Any questions? I know it was fast, but it's probably more like a review than anything else. So. Very good? Okay. Sorry, n by? It doesn't matter. You can invert. Basically, you can rotate one matrix or the other. It shouldn't matter. So let's. So again, this is a bit of theory, but also it has several fields of application. But let's take a look into something more concrete, like this kind of linear systems, where we have a matrix, a vector, and another vector, and we want to solve for x. Okay. So usually, if you have ax equal b, if there is an inverse for a, you can basically invert a and get x. Okay. This is mathematically true, assuming that this is the inverse of a. Numerically, one thing that we are going to beg you is please don't invert. And I hope that by the end of this lecture, I will convince you why not to do that. Okay. On the one hand, I can give you an advance. On the one hand, it's very expensive. On the other hand, it's very unstable. And if you want one more argument, if you have a nice matrix with a nice property like diagonals, it will destroy your sparsity, will destroy your structure in the matrix. Okay, but we're going to see this more in detail later. So the reasons I think I mentioned is slower than other solution methods like iterative methods. It's less stable. It ruins the sparsity, which is a huge memory penalty that you will have to pay. When we were discussing last class PD, someone mentioned, oh, that matrix is full of zeros. Do you actually need to save the whole matrix? And the answer is not. I don't need to save the whole matrix. I only need to save the non-zero elements. But if I invert that matrix, for whatever reason I had to, then it will populate the whole matrix with zeros. Okay. And as I mentioned, it loses any kind of a special structure in the matrix. So let's take a look at some easy systems to solve. Again, we're going to assume that there are no singular matrices in the sense that all these matrices has a well-behaved inverse. So there is exists a unique solution. That's another way to say it. But some systems are much easier to solve if we are aware of the special properties of the matrices that we are dealing with. So let's start by dealing with probably the simplest matrix that we may have. It's a diagonal matrix. Basically, the definition is all the elements in the matrix, with the exception of the diagonal, are 0, and there are only non-zero elements in the diagonal. So only the elements di j, where I is equal to j, are non-zero. And this is ridiculous easy somehow, because the matrix multiplication just reduced to do dx1 equal b1, dx2 equal b2, and so on. So in that case, the solution is you can write it straightforward, right? X of y, xi is equal to bi over di, right? So those are the simple. If you get this kind of matrices, you win. Another case which is nice, not as simple as the previous one, but still is a nice system, is what are called the upper triangular matrices. It means that only the elements above the diagonal are non-zero. Okay, so only above the diagonal with I greater or equal to j are different from 0, and whatever is below is 0. We are going to see that this, even when they sound sort of artificial matrices, they are not so artificial, because we can actually decompose a general matrix into upper triangular and lower triangular. So in this case, which it doesn't look so easy as before, we can still do something smart. If you look at the last row is pretty easy to solve, because UNN xn is equal to Bn. And then I have xn, and then I can go up and follow up and do back substitution. So basically, you start by solving the last row. The previous row is given by, you will have xn minus 1, and then you will have a contribution given by Bn minus 1, but you will have a contribution given by Bxn. But you had that one from the first row. So this term here can be substituted by the first one that you solve, and then cascade down, or cascade up, depending on what you want to see. That clear? So even the triangulars or upper triangular matrices, same applies to the lower triangulars, right? I could do the same trick, start by the first element. So even these guys are easy to deal with. Okay. These are a bit more elaborated kind of matrices, but they still have some nice properties because of some manipulation that we can do with them. These are called orthogonal matrices. Basically, what it means from the geometric point of view, or the matrix interpretation point of view, is that either the columns or rows are orthogonal between them. Okay, so they are linearly independent. The nice thing of the matrix is that the transpose of the matrix is its own inverse because of this orthogonality property. Okay, so when you transpose, basically you turn a column into a row, and when you multiply them, because they are orthogonal, you only recover the diagonal. Okay, so this is an inverse that we can actually compute without any kind of pain or anything. Okay, so orthogonal matrices are nice numerically speaking, and basically it's pretty easy to solve because you only need to, because of this property that the transpose is the inverse, you multiply the equation both sides by Q transpose. This is the identity, and then you basically solve the equation by just another matrix multiplication. Okay. Symmetric matrices. So the good thing of the symmetric matrices is that this basically repeat. So it's half of the work, right? So you solve for either the upper part or the lower part, and that's it. You don't need to do the whole matrix n by n. You end up with n times n minus 1 operations, actually, instead of n squared. So this can be generalized also to complex matrices, issues, but the only thing that you need to be aware is that when you do the transpose, you also need to take the complex conjugate. Okay. Okay, so within the category of symmetric matrices, there is a particular type which is called symmetric positive defined. And these are very common because the way that they are computed or generated appears when you do PDEs, like the stencil, or when you do when you compute covariance matrices or correlation matrices. Nice property is that they are always non-singular, because you can prove that the determinant is actually greater than 0. So that shows you that this is non-singular. Even more, you can prove that all the eigenvalues are positive. And the nice property is that it can be decomposed. You can show that it can be decomposed into a lower triangular matrix and the transpose of it. Okay, why is that? Because of this property of having this all eigenvalues positive, basically. Okay. What else? So we have seen some cases where basically this is what we mean with the structure of the matrix, the different forms that the matrix may have. The thing is that I mentioned sometimes you won't see directly the structure popping up in front of your eyes. But if you rewrite your equations, if you reformulate your problems somehow, that may be more evident. So in some cases, there is some work behind rewriting the equations such that you can see this. And whenever it is possible and whenever you find this kind of structures, try to preserve because it will make the job easier at the end. So let's take a look at some system properties in the sense of properties of the linear system that we want to solve. The first thing that we probably want to discuss is what is called conditioning or condition number. So it says basically it gives you a condition to know when the problem is sort of stable. This, if you look at the definition, if you look at the concept, it's kind of related to chaoticity somehow if you were dealing with differential equations. It is not the same concept because the perturbations here are due to the perturbations in the initial conditions for solving the system, but it's kind of the same idea. So it says that if I had a function f of x and I compute the function with a given perturbation, the problem will be ill conditioning if this is greater than 1. So if the perturbation over the x is a large number. In terms of numerically solving it, is hard to solve because we have seen that in some lectures ago that at the floating point representation, we will end always with some random, not random, but some noise in the numeric representation. This is just an example. How does the plot look? It's not so bad, kind of ghosty. So let's say I want to solve that system, 1, 1, 105, that's my matrix, x, y, and then the independent vector is 2. Okay, and if you do the algebra there, the equation that you get for y is x minus 2 or x minus 2 divided 105. Okay, if you plot those two lines, you can see they are kind of similar, but the important thing is that there is a large region here where they appear to be very, very similar. Right? So basically what this is showing this is that in some problems, when there are variations, a small variation of the numbers, you may end up with large regions of overlapping solutions. How to distinguish between each other is kind of is the tricky part of how to do it numerically stable. Okay, so a small change in the vector b can result in a small difference in the vector x. For instance, if you were solving for x here. Okay. What else? So the condition number is associated with the system. That's the main point. And because the system is somehow represented by the matrix A, remember the vector B is sometimes called independent vector, and we will see the linear algebra package that we're going to use will allow us to solve a system for several vectors at the same time. That's one of the nice things that those libraries have. So if I want to compute the condition number for a system, I have to look at the matrix that represent that system. A good idea of that condition number is to take the norm of the matrix and multiply that norm by the norm of the inverse of the matrix. So clearly this is not giving me the identity, but it's going to give me a measure of how the matrices differ between each other. Now the tricky part is that there is an inverse there, and I told you, try to not compute inverse. So many of the libraries, like LAPACK, already has routines for computing this. So when you want to know the condition number of a system, don't compute the condition number your own. Look at the routines. In this case is, I think, 3_corn for that. Okay. Now the other thing is, I think we are going to discuss this a bit more. The other thing is that the condition number is, that's the funny part. I don't remember if we talked much about this, but there are different ways that you can refer to errors when you're doing numerics. There is the relative error, there is the absolute error, there are the residuals, which we are going to talk about today. The idea of having the condition number is that it will give you a bound for which is the relative error that you can achieve in your solution. And that bound will be given by the condition numbers times the machine epsilon. Remember the machine epsilon we talked several lectures ago? So that will give you an idea of which is the relative error that you will achieve in your system. Okay. Okay. Oh, here we go. Residuals. Yeah, I mentioned this. So there are so many different ways that you can actually try to quantify the error that you do when you try to solve numerically the systems. There is the absolute error, relative error, and many more. The residuals, on the other hand, or on the same boat, provide an idea of which is the solution that you have achieved compared to the actual solution that you think is the right one. The nice thing of residuals is that I'm getting confused because in the other course we talk about residuals. So when you do a statistical analysis, you have residuals as well, and it's the same idea, it's the same principle. But we have residuals for differential equations, we have residuals for numerical implementations. We have a technique called residual independent evaluator, which is you have a problem, you have to solve it numerically, and you choose two different systems or two different ways to solve the problem, and then you compute the residual between these two. And the residual should converge, depending on the order of each of the system, to the largest order of the solution. Which is the best way to quantify this error? It may depend on the problem, it may depend on the technique and the algorithm and the implementation of the algorithm. Okay? So this is just some general remarks. So some good linear algorithms and their implementation should give you residuals no more than some function of the size of the matrix, that is very important, times the machine epsilon. Again, the error in X, this is a very good sign, shouldn't be larger than the condition numbers times that. Bad algorithm, this is a good one. Bad algorithm or implementations will depend on this, like the square root of the machine epsilon or worse, and it will be matrix dependent. Okay, so we're going to see a bit more examples about that. Okay, pivoting. This one probably you also saw in your linear algebra courses. The idea of pivoting is a method that will try to zero out most of the elements beneath the diagonal. I think I had a concrete example. The nice thing is it's kind of a game, so you can pivot as many rows or columns and try to do subtractions and additions between them so that you get as many zeros as you can. Yeah, and sometimes it's called PLU, factorization for pivoting lower upper triangular factorization of the composition. So, and these ones, why we try to do that? Well, we saw before that if we have these particular structures, this linear system are easy to solve. But also, I didn't have that equation. So if I want to compute the eigenvalues of a matrix, basically I'm going to compute the determinant of the matrix minus lambda times the identity matrix, right? And that gives me a polynomial of order, if this is n by n, this gives me a polynomial in lambda of order n, right? So the roots of that polynomial are the eigenvalues, and with the eigenvalues we can get the eigenvectors. So eigenproblems, yeah, I don't think I have the equation. Anyway, why is interesting to look at the eigenvalues? Well, if you are representing differential equations, basically those guys are the coefficients that goes in the exponential and give you the solutions of the differential equation. It tells you about a lot about the system. It tells you about the stability. In the problem for this week, you are going to be playing with the eigenvalues, how to compute the eigenvalues in different ways. So it will tell you about the stability of the system. Furthermore, when you compute the eigenvalues, you can go back to the equation and get the eigenvector. So if I substitute here a particular eigenvalue, then if I solve for x, I get the eigenvector associated with that eigenvalue. The ultimate goal is to write the matrix and have a complete decomposition, because I can take the matrix, I can take the eigenvectors, and then reconstruct the matrix using those eigenvectors. Okay? So it's bottom line is something cool, but also important to know about the matrix or the linear transformation, depending how you look at it. So for square matrices, again, this can be generalized, but let's just focus on square matrices. This is called similarity transformations. It doesn't depend on X. This is important. This is where things start to mix, and it's a lot of fun. But one of the things that you can prove, and these are, when I say prove, there are actual theorems that you can show, is that you had a full set of eigenvectors, meaning that all of them are linear independent, is when you can actually prove that you can decompose the matrix into diagonal forms. If that is not the case, then you can do something called Jordan canonical form, and that is pretty funny because instead of having only diagonals, you have like blocks in the diagonal. But this is not bad as neither. So the diagonalization of the matrix can be proved if you have n non-null eigenvectors. Similarly, the invertibility of the matrix. So if you know that your matrix has an inverse, then you can prove that. Basically, you diagonalize the matrix by doing this transformation where X is a vector formed by the eigenvectors, a matrix formed by the eigenvectors, and then the lambda matrix is a diagonal matrix. So that is called a similarity or orthogonal transformation of the matrix. Any questions? Sorry. No? Okay. So how to solve that system? We saw some special cases, but let's take a look into this in particular. And we're going to start by using the pivoting method or Gaussian elimination, if you want the fancy name. So let's take that matrix over there. Let's take actually that system over there. So it's a general matrix, doesn't have any particular form. We have x1, x2, and x3 being our unknowns, and then we have the independent vector 7, 6, 4. Okay. So one of the methods that we can use is Gaussian elimination. What is that? It's just doing pivoting on the matrix and independent vector. Okay, whatever operation you apply to the matrix, you do to the independent vector. So usually it goes like, okay, I take the first two elements, I want to zero out those, so I multiply or divide by 5 or 2 in that case, I add them together, boom, goes out the first one. I had to keep doing the operations with the rest, and at the end, after I think 2 or 3 iterations here, we end up with this triangular matrix here, this vector, the transform vector of the independent term, and that is it. And then we can do back substitution as we did before for the upper triangular matrix. Okay. Any questions about this? No? So the nice thing that we can show actually is that doing Gaussian elimination is the same as doing LU decomposition. And I'm going to take the same matrix as before. I'm going to do a very simple and silly thing. It's just multiply by the identity and write the same matrix because it's an equality. And then I'm going to apply the Gaussian elimination in both sides. Okay. And what I can show you is, okay, if I keep doing this, I didn't transform this one, but at the end you should get the previous matrix. What you will see is that this upper triangular matrix that we end up, if you multiply by this lower triangular matrix, you recover the original matrix. So basically, what we are doing here is decomposing the matrix into the lower and upper triangular part. Okay. So the method can be generalized or pseudocode like this. You start with the system AX equal B, you transform A into LU. Think about UX as a new vector Y. So now you have LY equal B. You solve Y by back substituting LB system. That's we know how to do it. We come back to the previous equation, and now UX is equal to B. Because U is an upper triangular matrix, now we solve X forward substituting the UY system. Okay, and so it can be solved quite quickly. Okay. Nice thing that I mentioned before, and in particular is implemented in the routines, is you can solve for the same I with different vectors P. because it's only show. So this bar is independent of B. It only appears here. So you can do that part very quickly as well. Okay. Okay, so we solve AX equal B. What about AX approximately equal? So, and again, this you may find either because your system has noise or because the representation and the nature of the problem that you are trying to solve. So, the thing is, not all the system AX equal B can be solved. For instance, consider an overdetermined system. Examples of this pop up every time that you are doing data fitting. And this is the example I have here. So this is a third degree polynomial with n points where I'm trying to fit that. And I want to have n solution for that. And even more, LU decomposition won't work in those systems because they probably don't have an inverse. So I cannot decompose. So what we do in those cases? And this is where part of the residual computation comes into place, and not only for evaluating how good is the method, but also to give us an alternative approach to that. So let's say I want to compute the residual of this system. So R squared in this case, I can compute as the norm 2 of the system B minus AX. Actually, this can be proved for any norm that you want to take in the system. So in the particular case, that can be written as B minus X transpose times B minus X. And if you do some algebra, you end up with an equation like this, which is nothing else, or it can be rewritten as this extra 2, you take it away, you put either one or the other term to the other side, and you end up with this kind of operation, which is nothing else that some particular decomposition or some particular multiplication, which is called normal equation. So, yep, sure. Where is the B square?
B dot or R squared.
Right. Good question. Did I miss that one? Transpose. Blah.
Find X.
Right.
Minimize R squared.
This is
R squared. Right. Oh.
yeah. There is an S.
Yep.
Yep.
Find the optimal value.
Yeah.
So first you want so exactly. It's just an approximation.
It's an approximation. That's why the approximation. The other thing is that yeah, this is the if you want to see is the generalization of the less minimal squares method. So basically, you take the derivative. Yeah. Is you substitute? Yes, I think so. So yeah, what you're saying is I have a x equal b, and you're saying if you substitute, I need the transpose, right? Yeah. Yeah. So how this will work? A transpose. Transpose x transpose. Yeah, there may be a way to do it. Right. Yeah, I think the best way to think about this is as Francis was saying, when you take the derivative because you want to minimize this. But there may be, I'm not saying no, there may be a way to recover that doing the substitution you are saying too.
Okay.
Noisy.
there's some. Right. What day?
Okay. That's right. Yeah.
This can be
Yeah. And the other one is a new vector. So basically what happens is, okay, I move forward into something else, but basically what happens is, as Francis was saying, this you can show that this is definite positive. So you end up with those kind of matrices, and this, whatever it is a new vector, call it C. So you end up in that case, and then you come back and substitute that. Well, you end up doing that because of minimization, right? But the other thing I'm noticing now is this should be called x tilde. So it's not the exact solution of x as it was originally proposed. You know what I mean? I mean, the perturbation may depend on B, but it's not the exact solution of the system. Okay. Any other questions? Yep. No. A is supposed to be this square matrix, as we had before. And let's say that is n by n, so we can do like 3 by 3 if you want. So this is going to be A, X we'll have here, and then B. But now, by doing the minimization of the residual, what we end up doing is doing A times A transpose times X equal A transpose times B. Now, this thing is going to give you a new vector. Let's call it C. That is a vector at the end. Because as n is n by n, if you do the transpose, it's still n by n. Okay? So you were saying about like it's n by n, so yeah. If A is right, but these are non-singular matrices, right? For this case, there should be some relation with the length of the vector, otherwise you cannot do the multiplication, right? No. It can be n by m, if that was the question. Yeah, it can be n by m.
Or if A is.
Yeah. Yeah. At the end, right.
I guess.
But at the end, this one is going to be a square, A transpose A.
Yeah.
Yeah.
Oh, yeah.
Yeah.
You reduce it to something that is square.
That is a square.
You could use the old method.
Yeah.
But I don't.
Yeah. Exactly. The A transpose A? You mean? No, you shouldn't.
Either white or.
Yeah. Independently of the form, this has to be definite positive, so it couldn't be singular, right? Oh, yeah. You're in the borderline, yes.
Right, but you could
Yeah.
imagine that all A is 0.
Yeah.
Somewhere in between you'll
Okay, so that talking about skinny matrices and so on. So we have the QR. So in this case, let's say I had a m by n where m is greater than n. So you end up with a matrix like that. Now the nice part is you can rewrite into a m by n matrix times another one that has only the upper triangular something part, like that edge over there, which is non-zero. All the y part is 0. Now, the nice thing of this, or the thing that you can prove, is that this QR decomposition, so Q on the one hand is orthogonal, and R is just this upper right triangular, if you wish. And you can prove that there is an orthogonal basis for Q that is of dimension n minus t. Okay? So the multiplication of these two give you A. But those, we know how to deal with them because of the orthogonality property and the triangular property. So in that case, if we come back to the equation, and I can rewrite A as QR now, well, the transpose reverse the order of the QR product, so I end up with R transpose Q transpose. But because Q is orthogonal, now we know that the transpose of Q is the identity, is the inverse of Q, so that is the identity right there, and then you end up with R transpose Rx, R transpose QTB, right? And basically in this case, R transpose is in both sides at the same place, assuming there is an inverse for R transpose because of the shape you know there is, you end up with this system. And again, this is a new vector, this is Rx, so you can solve for X and then back substitute because of the shape of R. Yep.
I think this equation is actually so. Is that the advantage of?
Yep.
Okay. I guess I couldn't see this applied. It seems like.
Well, this is this kind of matrix, right? You think about a triangular matrix.
Triangular?
Yeah.
Oh, okay.
That's right.
Okay.
So, and there are a lot of zeros there. So those are the matrices that we really like. So the R matrix is only zeros right here. So you end up here, and then you start to do back substitution, and then basically you get solution for X.
So if I try to take like ATA and try to like Gaussian elimination, that I would end up getting this.
I will say you should start doing this instead of trying to do. Oh yeah, I see. Yes. Right. Yeah.
Like
Gaussian elimination, unless that you hit a singular matrix, that should work. Yeah. Okay. Right. I'm going to talk about iterative methods in the root finding thing. No, that's how much is there? Like 17 slides. Okay, so we have been discussing direct methods, so basically manipulating the matrix and not obtaining a solution. But there are other methods, iterative methods, where you try to approach the solution by basically interacting or iterations. So successive approximations. The idea is that by the end you will be close enough to the order of machine epsilon to the solution that you want. So how that will work, and this one, at least let me talk about this one because this one you will use in the assignment. So it's called Krylov subspaces, or it's called also power method, and the idea is that you take the system and then you construct a subspace called kappa in this case. We will basically apply the matrix A to the power n as many times as possible to the independent vector. So the first one is A to the 0, so that's the identity, just give you the vector B. AB, A squared B, NA minus B, NA minus A, N minus 1 to B, and so on. What you can show is that by the end, you will converge to the largest eigenvalue. So you will obtain the largest eigenvalue by applying this method successively. Generalizations of this or further applications of this can be the orthogonalization method by Grant-Smith or Householder, where basically you start to project the components and you try to construct an orthogonal basis. And that will give you an approximation for the eigenvectors. This may sound expensive from the computation point of view, but it's quite robust and stable. So that's the nice thing. And it's not as expensive as solving complicated systems. Let's skip the Arnold iteration, at least for now. Another method that is quite useful, and that's why I thought that you may mention it in the root funding thing. So the conjugate, so this one, Francis is going to talk about why we do root funding, because It's basically useful for do root finding. There is a bunch of different methods, like the generalized minimal residual method that we discussed, but that's just generalization. And there are some links there. Just let me mention about sparse matrices, because we talk about these ones, and they will show up a couple of times. So the idea is that you have a lot of zeros, and the question is why I should store all that data instead of just storing the non-null elements. And the idea is that it's worse to do this when the number of non-null elements is at least over 10% of the size of the matrix. Okay. Why we discuss all this is to remember when we did the PDEs, we discretized the equation by using Taylor expansion, and we end up in an expression like that. And then you can have cells or nodes or points of discretization, and your equations will be expressed only in those elements, right? And if we use that, we may end up with a matrix. This depending usually when we do PDEs, we call this a stencil, but it's basically the same. It's representing just the final different equation representing the second derivative there. So you end up with what is called a banded matrix. All what is outside the diagonals and sub-diagonals are 0. And then you have basically 1 at both sides and -2. And the special conditions, we talked about this last class as well, are the boundaries. So for the boundaries, we can do different kind of things. We talk about Dirichlet and von Neumann conditions. Depending on which one you have, is the condition that you're going to impose in the boundary. But those are reflected in principle in the first row and last row of the matrix representation. But it won't affect the other terms. It's still a banded matrix at the end. So this was one of the theses of the beginning of the class. Is if you want to compute the inverse, you will break the sparsity of the matrix. So that matrix is a smaller matrix representing the stencil of the differential equation. And this one is a way to split the matrix into lower diagonal and upper diagonal. You can do the algebra and check that that is the case. Now, if I'm going to compute the inverse of that matrix, this is what I end up with. So it's a matrix that basically doesn't have any zero at all. So I went from a banded matrix with diagonals and subdiagonals, and now to a full populated matrix. Okay, you can imagine, and this is for what? 5 by 5. You can imagine this goes as n squared with your problem, right? As many points as you have. So instead, you can do LU decomposition. In this case, you end up with these subdiagonal matrices. This is a particularly good example, but in any case, it's always better than the whole inverse matrix. Yeah, don't worry. I think mentioned 10% of zeros, blah blah blah. Because these sparse matrices are so common and so well used, you have particular or special file formats where you can actually store that. Actually, what we are going to see is that, in particular for banded matrices that appears a lot in these partial differential equation problems, the routines that we are going to be using in the library are special for that. There are special routines that basically triggers or target this particular matrix. Okay. Almost done. Let me just show you an example of an application that goes beyond math, if you wish, or not beyond math, but is with us every day. Is how Google computes these PageRank algorithms. Basically, when you search in Google, is how it categorizes the responses that they give you, and this is based on this PageRank algorithm. Basically, each website or each HTML site or website internet is represented by a graph, and so the links between the websites are represented by connections between the nodes. And what they do is basically they create a matrix, and the dominant eigenvector of the matrix give you the rank in the order that is showing you the solutions to your search. So for instance, in this graph, let's say you have a designed education website that points to the course, and the course points to the wiki, and the wiki points to the main website, and so on. So these are the links between the pages. The way that you construct the matrix can be normalized or not. In this case, it's normalized, meaning that each row, if you add all of them, give you 1. But this is just a normalization factor. Can be normalized or not. So one nice thing is that you create your graph or your connectivity matrix, as it's called. That is the matrix representation. You start with a given vector. I start with 1 over 4, 4 times. This is equal probability if you wish. And then you start to iterate. You multiply the vector once by the matrix, twice, and so on. You construct the Krylov subspace, and you end up with this vector, which is the largest eigenvector associated to the eigenvector associated to the largest eigenvalue. Okay. There are different ways that you can interpret this procedure. In dynamical system, this is the equilibrium of a steady state that you will reach. In linear algebra, this is like the normalized eigenvector. You can think about this as this system of equation where you are solving for the steady state of the equation, and basically you end up with the same equation. And in probability, you can think about this as a random walker, wandering on the node. And so you start, as I start there, with equal probability, 1/4, and you end up with that solution. Okay, I think this is it. Yeah, and this is, if you are more interested, this is how Google computes actually that matrix. Okay, just mentioning this because it's kind of related to what you will have to do for the assignment, and also to the Krylov subspaces. Any questions? I know it was fast. Like, how many slides, Jesus? Yeah, I don't know. Oh, okay. So next lecture is like the packages, how to do this. Yes. Yep. Did I say that? Let me see. Is unstable, you remember? For computing the largest eigenvector, I guess. Yeah, that's what I thought. There may be a typo in my slides. I was tired yesterday night. Let me see.
I think that part of associative now you want to find doesn't take a large. So you're going to figure out what is my part. Check that out. Doesn't hold. So have that base part.
Yeah.
Okay. So that's the mathematics. The problem is we're trying to get that stuff.
Yeah.
That if there's all of both so this idea works for a couple 5 minutes.
Yeah.
Okay, but never get all the eigenvalues away because by way
Your system has changed.
And value iterate. Okay. That's so it's very stable for the large.
For the, yeah.
Okay, for one or
It depends on the
then
system.
it's not as stable. Better ways. All the eigenvalues. But large is better because out of the and if and how you have
10 iterations.
so each of so look at cases. K has n vectors. Set it n dimension. Represent shape. Right. Also, and instead, even if my original key, you can see how it's very efficient. Fast, large. Good take. this is a way. Large.
It also is true that in many cases it's only the largest added value that determines the behavior of your system. So if you're looking at dynamical system, it's just the largest eigenvalue. Stability is the largest eigenvalue, right? Yeah.
That's right. Some space.
Yeah.
And you could be clever about by transforming a, for instance, getting one of the market policy.
Yeah.
The largest. And they.
Yeah.
But some along the line.
Like a linear mapping or something.
Come out. There's friction in point for that's better way. Yeah, but I play if you're rather than well,
Yeah.
they'll be far.
Well, the Grant-Smith method is based on that.
Yes.
It's based on getting the eigenvectors.
And it suffers from
right.
Out. So that's how you
Eigenvalues and eigenvector computations is.
Yeah. There's a lot of care.
Is people doing research actually in preconditioning problems. So. You will have a nice assignment to play with the Krylov space and something else. Any other questions? Yes.